Okay, so let's start. Lunarc is here at Lund University, the Scientific Computing Center. Started 86, quite a while ago. We're a member of SNCC. SNCC is the National Infrastructure Committee, funding the computer centers, the 6 computer centers we have in Sweden. So it's Lunarc, and then we have Göteborg, we have Linköping, Stockholm, Uppsala, and Umeå. So quite widespread. We have at Lunarc 3 applications experts, of which I am one. The other one is Joachim Hein, who is mainly focusing in Fortran programming, OpenMP, MPI, that kind of stuff. And also we have Roger, who is doing more user-specific tasks, working in projects. 5 system administrators and 2 directors. Apparently we are quite a wild bunch, so we need 2 directors. Also, we provide HPC resources for Swedish scientists and research groups, and also we have a pilot project now trying to provide computer resources for Nordic researchers. We'll see how that goes. That was the meeting I had just before this. So, what do we have? We have a cluster of servers, which is Aurora, got 20 cores per node, 64 gigabytes of RAM per node, roughly 3 gigabytes per core to run with. And that's a limitation, and you will run into this. We have a fast interconnect, which is an InfiniBand connect, not the latest, but the second last latest. We have a really large storage system. It's in the order of half a petabyte. And we have also K80 and K20 use on a subset of nodes. And those are only available for the ones who have local LU projects, because SNCC is not funding those. Right, so how to get access? You apply through the SNIC site, which is the super site. Apply for a project at that site. Once you have a project, accept the user agreement and apply for an account, also at the super site. And that gets sent to us to create your local account. Not very strict. How to get access to the resource? You need to have, today you need to have a mobile phone, because we use 2-factor authentication. So you log in, you get a second password sent to your phone, and then you're in. We will change that into a token-based system, sort of like Google Authenticator or something like that. And that will come during the spring or summer of next year. We have a graphical front end. We have ThinLink, which you can download from the Lunarc web pages, or rather follow the link there and you get downloaded. You can file transfer, you can do using SCP, WinSCP and Windows, CyberDuck on Mac OS. Or you could just use SCP if you're familiar with the Unix commands. For support, you use the Lunarc web pages. We have a lot of information there. Basically, most of the things I'll be talking about will be available there. You also have the support form where you can send in a support question. You will get a support number, and the support mail will be received until the problem is solved. We'll go back and forth on that. Do not reuse an old support question. If you have a new question, send in a new support question. If you reuse it, it might have been closed, and it might take a while before anyone sees it. Right, so why would you use Matlab for HPC? Well, it's familiar. You know how to use it, I assume anyway. It's portable. Prototyping is really fast. You can conserve the licenses, because you don't need to use as many licenses when you're running on the cluster, because all the worker nodes inherit the licenses that you use. So if you have 2, let's say you have 2 licenses for the optimization toolbox, you are using 1. Starting the job on the worker nodes, you're still only using the 1 license. So some other one can use it, which is a good thing. It's really fast if you use it on a cluster. And you have a lot of packages and code, so people have done a lot of stuff. So you don't have to do it, which is a good thing. Right, so the MDCS, which is what we are going to be using, is using the MPI message passing interface. Do you know what that is? Right, so the basic idea is that you have a network of computers that talk to each other by sending messages. These messages are packaged and sent by you as the programmer. In your program, you package those messages, and that's being sent off to the other nodes, and they receive them, and then they do your bidding, as it were. So they're using the MDCS with MPI to scale out the parallel computing toolbox, which you always have. You can run in parallel on your laptop or your desktop machine. I think it's up to 32 or 64 workers you can have now, which is quite a lot, actually. So you use the PCT when you're running on your local machine, and there you have a license for that every time you have Matlab. The MDCS license is not certain that you actually have. So, as I said, the workers inherit all the toolbox licenses from the submitting process. That is to say, any toolbox you have, your workers will be able to use. Regardless if you have 1 license or 50 licenses of it, they will be able, so as long as you have one, all of your 500 workers can actually use that same license. So the only thing you need is the Matlab and license when you submit your job. After that, you don't need anything. They know what they have, or you have. So these constructs, the PCT constructs, they scale seamlessly. That is to say that if I'm writing a code on my laptop, I can use that same code on the cluster because it scales like that. Of course, you may have some considerations that you are taking into account when using your laptop. You can do more tricky things if you have more workers, but basically it scales. And you can prototype it on your local machine and then just move it over and then you run. The setup they have in Finland is that you actually start your Matlab process on your laptop, and then you connect to their cluster and use those as workers only. Whereas here, you log on to the system and you start Matlab on the cluster as a graphical front end. So it's available on the desktop and through the terminal. Terminal is the black hole with all the text console, right? The desktop in this case is a windowing system. It's integrated with the queuing system, so you don't have to think about that. You don't have to write to submit scripts. Everything is done for you. It distributes workers in a parallel pool. So the parallel pool is the critical concept here. That's the concept you need to know. And you can have up to 500 workers. Now, I say that with a caution. Try not to use 500 workers, because 500 licenses for the MDCS, the parallel computing in that sense, is what we have in the entire country. So do not use that too often. As I was preparing these lectures, I was going to test something last Friday evening. So I logged onto the cluster, started sending off jobs, and they failed miserably because someone was using all the licenses, or rather one was using 430 licenses and one was using the remaining 70. So I can do anything. That's not a nice situation. 100 workers is quite a lot. Right, you can use larger memory and more cores. One core corresponds to one worker, that is. You can use a GPU if it's available to you. You can distribute arrays over all the workers. So if you have 50 workers on 50 different nodes, you have 50 times 64 gigabytes of RAM to play with. That should cover most of your needs. You can run applications interactively or as batch jobs. So, should you use the desktop or the console? For full MATLAB interface, Lunarc desktop is recommended because you get this nice graphical environment that you're used to. If you just need to send in scripts, you can make do with the console. It's not really a problem. You just want them to create a file or do something. The Lunarc desktop is run through the Thinlink client, which is available at Sendio Thinlink download, and it looks like. Let me see. Let me do this. So I will switch over to. First, I need to switch to the PowerPoint. No, to. Where am I? I'm there. To that. And I need to change this screen sharing so I can show the screen I want to show, which is. Sorry about that. I want to share the screen, which is this one, and then I'll go over to that. Yes, that's the screen I want to share. This is the Lunarc desktop. What I've done here, I've just started it. You can see on the top left corner, you see applications and places and system. You have a web browser. You have can start a console. The console is where is my pointer? There's my pointer. So this is if you want to start a terminal, and then you get this one, which is the terminal. That is a fully fledged Unix system. So Linux Unix. So that is what you are going to use, and you can see the name of it. It says on the top mid of the midsection of the window there. My username at Aurora RVis01 Thinlink client. That is what you are going to use. Now let's see, where is that? Was over here somewhere. Will be there. There it is. So now I stop the screen sharing and we go back to sharing the screen again on the PowerPoint. And we start. And there's the PowerPoint. Right. So when you log into the Lunarc desktop, you get this window, and you need to add the name of the server, which is aurora.lunarc.lu.se, your username, in my case, Hukibuck, and then you add your password, and you get a second prompt to enter your OTP, which is sent to your mobile phone. You enter that, and you're presented with this rather nice desktop. That's pretty easy and pretty standard. The third way to start MATLAB on the Lunarc desktop is using the menu system. So you click on this applications menu, Lunarc applications, go down to MATLAB, and you get this list of MATLAB installations. Now, you notice that they are repeated. Well, not the 2014A, but 2016A, 2016A, hardware OpenGL acceleration, same for 2017A, 2017B. That hardware OpenGL acceleration was true until 5 days ago. Now it's called GPU enabled. And the difference is because there's a bug in MATLAB which cannot make use of virtual GL for graphics acceleration. So you do not get the really pretty graphics that you would get on your normal desktop. But on the other hand, you have access to a really large machine and with GPUs. So if you want to use GPUs, you use the hardware OpenGL acceleration. The name will change, but that's the one you should use if you have access to GPUs. Right, so when you start, now I've started the 2017B hardware OpenGL acceleration menu joint. And then you see it says up here on the midsection of that window, it says on GFX 0. That program has actually been started on a different machine. The name of that machine is GFX 0. That's important to remember, because sometimes when you set up the Matlab, which you do like so, configure cluster, that is run on the GFX0. So the profile setting it up is run on the GFX0. That may or may not be the same or a usable profile on the ARMVis01, which is the node you log into originally. So that's why you should use the same version of Matlab when you choose in the menu. Choose one, use that, because you may run into problems when it saves the files. Now, the first thing you do, if you've never started Matlab before on the cluster, the first thing you do is to run config cluster. And it's spelled exactly like that. The second C is capitalized. It will wait for a little while, and then it'll come back and with an informational text that says you need to set project name and wall time before submitting jobs to Aurora. And it gives you information on how to do that. So you need to create an object called parcluster. In this case, we call it C equals parcluster. You set additional properties. One of the properties is the project name. As a string, your project name. I will show you how to find out your project name if you do not know that. And also the additional property wall time. In this case, I've set it to 1 hour, 010000. So it's hours, minutes, and seconds. No point in setting it to 2 seconds.
Sorry, excuse me, Anders.
Yes.
This is needed just for Aurora, or is it in general?
This is in general for all Matlab installations. You need to run, the first time you run Matlab, you need to run config cluster for each version of Matlab. So if we upgrade the version, which we will do in the spring, to the 2018A, you need to, and you start that, you need to run config cluster for that version.
Mm-hmm.
Otherwise, it doesn't have a profile. It will run locally, and we will come and tell you off. Because when you run locally, you run on the node that you are logged into.
Mm-hmm.
And you will not be. Right, and then finally, c.save profile. If you do not save the profile, you shall have to do this every time you log in. No fun in that. Now, for the Lunarc desktop, I did this. I set up all that. And for all the installations, you use config cluster as before, but you say cluster info.set project name, .set wall time. So the command changed from 2016A to 2016B, I think it was, or maybe between 16 and 17, but that's the old way anyway. The new way, it's much nicer because you have the object, your par cluster object, and everything is contained there, all the methods and the functions. Right. So how do you find out your project name? This is valid for Lunarc in the Aurora system. I do not know how it is at HPC2N or in Uppsala.
It's the same here in HPC2N.
Okay. So you use proinfo, and notice that I have exclamation mark before. Exclamation mark in Matlab means run this, the terminal, as a Unix command and give me back the result. So bang proinfo gives me what projects my user, is registered on. I'm registered at Aurora Test, 1, 2, 3 SNCC projects. These SNCC projects, or LU projects if you are local users, are the ones that those names are the ones that you put in the string project name. Having that, then you can send in jobs. If you want to see the additional properties that you have set, you just type c.additional properties. The answer will be what properties you have set. You can set use GPU. You can have, if you want to have an email when your parallel pool is started, your job is started. and when it's finished. Lots of things that you can set like that. The old system of doing that was this: set arc, set cluster host, set private key file, and so on and so forth. So that's cluster info.set, one of those. That's the old system. Right. The workflow. This is trying to illustrate the local. If you use the profile local, because when you run cluster, config cluster, it creates a profile for you. One profile that you always have is the local one, meaning the machine you logged into, that host. So you have one master process telling the other workers what to do. That's running on the local host. Now, there are a lot of other people running on that host. So they won't be happy if you have a lot of workers dancing around and doing stuff on your profile or on that host. That's why you use either the interactive. Here you have started a parallel pool on one of the nodes. They are running on a remote host and they are controlled by the user process more or less directly. You write on your local host R4 blah, and that gets divided up on the workers on the remote node or nodes. Or you can run it in a batch where you have the local host, you have your master process, it starts, works in jobs on one, or in this case, 4 different nodes using 3 processes, and one of it has, they all have their own master process, so you always have to start one more worker than you are actually going to use, and that's controlling the jobs that the others are busy doing. Right, so dispatched, and each of these have their own job ID in Slurm. So if you want to have a look at what's going on, you can just look that up. And in Matlab, you have that, what's it called, the job, manage jobs is called, where you can see all the jobs that you have running currently. Because you can have an infinite number of jobs. Or rather you can't, because you can only have 500 jobs. But, well, there you go. Right, so how do I share code with the workers? Because I want my workers to do something. Well, they can either access files directly, and that's the way they use the toolboxes. They access the toolboxes directly because they know the path to them, so they can use them. Or you can pass data to and from worker sessions. That is just sending off the data you have. You create a, if you have a spin process, you can start and you create a matrix that's distributed over a number of nodes, and then they have their data there. You can send it in your call, additional files, and tell them where these files are. Or you can pass Matlab code for startup and finish, something that you always want your workers to do when they start and when they finish. Let's say that you want them to create a number of directories when they start that you want them to fill out, and then they want to pack them up and send them off to something when they are finished. That you can always do. So how do you start a parallel pool? Having your cluster profile, the Aurora 2017A local profile, for instance, having that, you just type parallel pool and then the number. That will start a parallel pool on the cluster. Now, we had a power outage yesterday on the cluster. So I can only log into the cluster, but I can't start anything because the nodes are down at the moment. Otherwise, I would have shown you how to do this. But that starts a parallel pool of n workers. That's where you put in 2 or 500 or how many you think you need. And then, or you can, if you have a script called script1 in this case, you can start a pool, hence the code word, of size, in this case, 8. That starts a pool of 8 workers, and it runs the script 1, on those workers. That could also be a function. You could have it at magic, for instance. That would create a magic square on those, distributed over them. In your case, I call this J. You could call it anything you like, but that's the handle to your job. So J will have a lot of functions, like j.fetch outputs returns the outputs of the result that the script created. You can have j.wait, then it will wait until that job finishes, and things like that. So how do we do it when the workers access the files directly? Well, they all have access to the same drives on the network, so they can, anything that you can see on your local, when you are logged in, anything you can see, they can see. They can access those with the same read-write rights as you have. So in essence, for all intents and purposes, they are you on the cluster. You could also have a job, and you can have, like when I said in this batch in, you can have a flag called additional paths. There you can set the property and tell them the files that are in this directory you are going to use. Or you could have a path command in any of the startup files for the workers. Here in the toolbox local startup and the discount user job startup and task startup, there are example scripts that you can use to create scripts or things that you want every local worker to perform every time you start, if you want to do that. Right? Am I going too fast or? All right. You can pass data to and from a worker session using input and output arguments. And you can also have job data, which is you say that on the internet there's this database that you want to use. The data is there. You put job data as a property of that job object, you can access it. This is very handy when you are working with, say, a Hadoop database. Let's say you have a database of terabytes. You don't want to move all of that directly. You can use the Hadoop framework to do a MapReduce call to the database and get your information back. So Matlab is Hadoop enabled. You can have attached files. These are of the job object, also a property of that. There, you, as a cell array, you specify all the files and folders that you want the worker to have access to, and that gets sent to that worker, or rather, the pointers to that get sent to the worker. Same thing with auto-attached files. If you wanted to have something you always want to have, then just have the auto attached. Right. So you can pass code from startup and finish, because it always executes this startup.m, and these are the ones that I told you about a bit earlier. Anything that's in the startup.m file looks at that, and where you started the job from has precedence. So if it's there, then you run that. If that's not there, it will run the one that in the toolbox. It's not in distcomp, it's in the toolbox local, I think. Anyway, these can set up and clean out and do stuff for you. You don't really need to clean up after yourself, but if you've written to your home directory, maybe you want to. But you don't have to worry about files that have been created on the nodes, because those are blown every time your job is finished. So you don't really have to worry about that. But it's a good practice. Yep.
Hang on, back up, please.
Yep.
a worker session executes its startup.down. So is there a directory or a file associated with each worker?
Each worker will get a...
What do you mean with a worker session?
Let me show you. Let's do this. So I go over to, and then I need to find where you are. There you are. So let's share the screen of the thin link. You see the thin link now, right? I take that as yes. Right, so can I make this terminal bigger in some way? Let's see. Let's do that, and then can we increase the font? No. No. Does anyone know how you change this font size in this?
Zoom in, maybe. You did zoom
you can press Control and plus.
Yeah. Yeah.
Control plus.
Yeah, I see it. Thank you. Like so. Can you see the text there?
Yes, I can see that.
All right. So now in my home directory, there's a lot of files here. There's particularly one important file called MDCS. Where is it? Ah, there. MDCS data location. This one. So if I go into that, I see I have the Aurora and I have the Lund. If I go into the Aurora, then you see I have Aurora RVS02 and the GFX0. That indicates that I've run the config cluster both on the GFX0, which I just did. I showed you the slides of that. And I've also run it when I started directly on the RVS02. So let's go into the GFX0. Then I have R2017A and R2017B, the versions of Matlab. So let's go into B. Then I have local, so I go in there. And there, you see, I have jobs. In this case, only job 2. Here's all the information of the job 2 that Matlab has created. So I go into job 2, the directory of job 2 there. Now, here you see tasks numbered from, I think, 1 till 12. That means I've had 12 workers running, performing a task. Each of these have created their own files. So if you look at task 5, common, diary, in, job out, out.mat, state, common, state was the last one. Those 5 files are created on the node of the cluster where the worker is running. Those files are local to that node, to that worker. And they get copied back into this job directory once the job is finished. Now that has some impact. If those files are large, this copy will take some time. You can't stop it from copying them, but then you would have problems getting the information or the data back that you really want. And if this takes a bit of time and you try to access the results before the files have been copied back, you will not get any data, or you might get the wrong data. That's why you have to use the job.wait function so you see that it's finished. You get the reply finished if you type job.wait or job.state and you see finished, then you can get data. Then you can use the fetch output. Right? Did that answer your question?
No, not really, because where is the startup.m?
The startup.m is read by each of those nodes.
Yes, but where is it?
I would have put it, let's do this. Now I'm in my, no, I'm not. Let's do just a CD. Now I'm in where I have my files, so CD Matlab test. Is it called? Oh, there. Here's a directory where I've done some running. This is where I would have put the startup.
But that is the regular local startup.
Yes, that's the regular local startup.
It wasn't a PowerPoint. It appeared as if it was a special node-related startup file.
You can have information in there only because you want some things to do all of them, but you can also have things that you just want that worker to do.
Yeah.
And then you check the worker ID of that one, and that you can have in that as well.
But that's something I write in the...
You write that in the startup, yeah. So you check, which one am I?
Yeah,
do this. So let's go back to...
And excuse me, what is the content of the start tests file?
The startup file?
The start tests.m.
Yeah, I can show you. Cat start test. That's just a MATLAB file doing testing the startup of a pool of workers. So I have C dot equals par cluster, number of workers equals 3, number of simulations equals 10. I have a job, C dot batch, parentheses, at par4 test. Par4 test is a parallel 4 test loop that I've just written. It takes one argument in, which is the number of it gets one argument out. And it also gets the number of simulations, the 10. I have it as a pool, and the pool size is non-workers. Then I have job.wait, waiting for the job to finish. Then I have displayed, waited long enough, so I have waited. And then I get y.out job fetch outputs in the in a cell. And then I just, I will have had a catch error as well before. So that's just a test program, really basic.
Okay.
Right, so where am I? I should be there. And then I need to stop the screen sharing. Where is my, there's my, there you go, and do that. And we go back to our PowerPoint. That one should be somewhere around there. Right, and now you see a PowerPoint. So that was the job startup. There's one task startup as well for each worker, each time the worker begins. Or you have a pool startup if you start a new pool. A task finish if you want to remove stuff, and so on and so forth. There are empty versions of these that you can have a look at in the discom file. And I say that you can edit these files to include whatever MATLAB code you want. That is true, but you need to copy it first. Don't edit it where it is, because then you ruin it for everyone else and no one is happy. Right, so what to do if you have slow code or auto memory? Well, obviously you need to know your enemy first. You need to know strength, you need to identify the bottlenecks and exploit data and task parallelism and find the best trade-off between programming effort and achieving your goals. How do you do this? You use the MATLAB profiler. The MATLAB profiler is your friend. Has any one of you used it before? Peter has. Yeah. Start it up, run your program, you will get a report on where it spends the most of the time. You do this for your serial program. Before you do anything in parallel, you optimize the serial version first, because that's much easier. Having done that, then you can look at, oh, I do this code. Let's say I do a ODE 45 million times with different starts. Well, okay, then parallelize that, for instance. Right? So, and test your code locally on a small program. Don't try to save the world. Just save your local bits. And then you use the profiler, and then try not to use, well, I really talk about that, but if you start up your parallel pool, then you can start type par4 and all that in the console and run your programs. That's really inefficient, because most of the time the backend will wait for you to type. So write the script, send it in through batch. That will be much better use of the system. And Matlab on the desktop as a launcher through the batch command. That's what you would do. Now, let's come to the funny parts. I have two speeding up Matlab flowcharts. I'll just skip through those because we've gone really long already. So let's have a look at Paralyzing Code. This is an interactive run with the loop in parallel. We have a serial version going 1 to 1024, do a sine calculation, a waveform, and then you plot it. And the only difference between these two is that the one has par4 in the beginning, the other one has 4. Par4, what that will do is it will chunk up that array of 1024 iterations into how many of worker nodes you have. And then it will run those locally. And it will get back there. That one will scale fairly well. Now, this is the construct. The normal for loop, start value, end value, some statements, and end. Par4 looks exactly the same. The only difference is these 3 letters par in the beginning. There are, however, some differences. In the for loop, you don't have to be consecutive, because that is just a vector, and it goes through the vector and pick out the values that are there. Use those in here. This vector could be 1, 5, 3, 8, 11, 17. That would work. In par4, they have to be consecutive. You cannot have a vector where you jump back and forth in the indices. Has to be consecutive. Now, variables for par4. You have a loop variable, which is your loop index. You have slice variables. That's segments operated on by a different iteration of the loop. So you get that section, I get that, so on and so forth. You have broad variables that's defined outside the loop, that you need inside the loop, but you never change them. Think as in Fortran you have constants, for instance. You have reduction variables that have a value that accumulates across the iterations. Doesn't really matter the iteration order. I have temporary variables created inside the loop, never access outside. Looks kind of like this. Here you have I equals 0, z equals pi, z equals 0. R is a random vector from 1 to 10. Par4 from 1 to 10 over I. A is a temporary variable here, gets the value I. That's a loop variable. The Z increases with whatever I is. That's the reduction variable. B is the output variable, and that one is sliced because worker 1 has some values for B, worker 10 has some other values for B. R, in this case, is the sliced input variable. The values here of R, let's say we have 2 workers. The first 5 of R are sent to worker 1. The last 5 are sent to worker 2. And we have a broadcast variable C that's never changed, pi. So if I is less than or equal to pi, do the calculation of D, which is a temporary variable. That one will be lost. The value of that will be lost. Right, so what if my loop is nested? So here we have a magic square and a square of zeros the size of the magic square. So we loop over that, we do some calculations of it, and then we stop. Rather pointless program. But it has nested for loops of X and Y. If we do that, and we parallelize over the outer for loop here, of the X part, you get a runtime of 0.4 seconds. If you do the same, where you parallelize over the inner for loop, do we get a longer or a shorter runtime? Any guesses? What do you say?
Longer.
Yes, you win the prize. There you go. It is dramatically longer. Almost 10 times longer. Because you're parallelizing on the wrong place. So, if your loop is nested, the body of a par for loop cannot contain another par for loop. You can't have par for within par for, with one exception. You can call a function that contains another par for loop. So you can have a par for that then have a par eval, for instance, or have another function that has a par for loop. But as it is running on within the par for loop, it's running on some node, on a worker, and workers can't open a parallel pool. Therefore, the inner nested par for loop will not be run in parallel. It will be run in serial. So only one level of nested par for loops can run in parallel. If the outer loop runs in parallel on a parallel pool, the inner loop runs serially. If the outer runs serially, then the inner loop can loop in parallel on workers within some pool that you have access to. And the body of par for loop therefore can contain 4 loops. That's not strange. And you can use the inner loop variable for indexing the sliced array, but only in plain form. Only like this. You can't have it as an expression here.
Is there a way to collapse the loops as in OpenMP?
Yes. Not really. You can, I mean, you could always change these into vector notation.
Mm-hmm.
And that would, that way you could expand it so you have only one for loop. But it would be very hard work to do. And I do not think that you would win that much on it.
Okay.
Yep. Right, so here's another example. The left one is invalid. The right one is valid. Anyone can see why the right one is all right, and there's a prize on it to be had. The answer is in what I just said in this previous slide. You see this on the valid side, you see this n, which is the size of A. That is set as the limit of the J loop, of the inner loop. In the invalid one, I calculate the size of the for loop depending on the size of the A, which I do not necessarily know in that case. I can't be sure that I know that size. That's why I can't be sure how large will this par4 loop be. And that's why you can't run that. Yep.
Is this because it's Matlab? Because any optimizing compiler would fix that.
Yeah, this is because it's Matlab.
Yeah, so it's peculiar to Matlab.
This is peculiar to Matlab, yes. But I wouldn't recommend to have it, even if you have an optimizing compiler, because it might come back to bite you in the ass. So the range of for loop nested in powerful must be defined by constant numbers of variables. It cannot be something that's not constant, that's not known. So that's why you work around that by stating the size here explicitly. Yes?
But is it invalid or is it just not running properly?
That will be invalid.
It will be
that will crash. Yeah.
A crash, not an error.
It will
be a runtime error.
It will catch up to that. It will catch up. Yeah, it will see that. But it's another chance to win a prize. The right-hand side is correct, the left-hand side is incorrect. Now, why is that? What are we slicing in this case? What is happening in this loop is that we are looping over something and we are going to chunk that out to our worker nodes. We don't know where to write in this. We don't know what the size is in this case. Here. You need to know where those things are, because the sliced array there, you may actually end up outside of that. In this case, you never change these, the I and J. You know what they are beforehand. So that means that you know that these are within the chunk that I actually have when I parallelize that, or the compiler does that. That's why the right-hand side is valid, whereas the left-hand side is invalid.
I don't really see that. Why can we know what, for example, I plus j is in the right-hand side, but not in the...
This is just a value. This becomes a value.
But you can't use values as indices. Is that the great problem?
You can't have something that you don't know beforehand what it is. In this case, you know what these will be.
And if I have a temporary that I say I plus j, and then use x, and then
that needs to be stated outside.
So temporary variable cannot be used as an index either?
No, not in that sense. So it can't be a partner expression. So, another chance to win. Fabulous prize.
Just back up again.
Yep.
So the reason we call it sliced is that you do not transfer the entire array A, just transfer a slice of it to the worker.
Yes.
But that's why it's called sliced.
Yes. Like a loaf of bread, you slice it up, you hand it up to the kids and they eat it.
That figures.
Right, so this one then. Why is this one not correct?
So you just displayed the first element of the certain row, but you parallel it.
Let's see. You have a nested for loop index to index into a sliced array. You can't use that array anywhere else in the for loop. On the left-hand side there, it doesn't work because A is sliced and the index inside the nested for loop. The code on the right there, the V is assigned outside of the axis of the nested loop, and then you actually can do it. So it's great. You win another prize. Right. So I have a lot of these examples, and there's a lot of those examples in the MathWorks web pages. I urge you to have a look at those because those are very good. I will also have these slides available online. So I had a parameter sweep example as well with the sweep speed up. The par eval is quite important actually. Have you used eval? You have a function and then you evaluate the function with some of the numbers. In this case, I have the function round, which is a built-in Matlab function. Takes an argument and produces a result. So I send in the function and my argument, which is pi, and round that equals to 3. I round this one. I have another. The function round can also tell me how many valid decimal places I want. So I can just type that in, and then I get 3.14. The par eval, basically the same thing, but it's just on a parallel pool of workers. So I can have par eval of my output, my pool, and then I have a magic square of that size, 1 to 10. And the value would be fetch outputs of my F object, my batch object, my job object. I get the job back. So par eval and feval work in basically the same way. The only difference is that par eval does it on a number of workers. Yes?
This is very similar to how you use batch.
Yes?
What's the difference?
The difference is that this is a function evaluation. You need to have a function only. A batch can have a script, which can call a number of other scripts. And you can send in much more things to a batch than a par eval. That's.
But if I just run a function on batch, it's the same.
Yeah, if you just run a function in batch, it would be more or less the same. There are some caveats as well. So this is a par eval example. In this case, we have a function called test on a pool with 10 million iterations. And I have this IDX, which is the index, the job index. So I have a number of jobs over those. So I send that in. And then I wait for them to finish. So I have my output. So in this case, I've started 6 different jobs, all doing par eval of this test function. And then I can wait for them and fetch the next jobs. And then I get everything back. This is a completely legal way to use the system. If you have started a pool, so you're running on the back end. If you are using the local profile on the front end, you will be told off. So then there's a lot of more things to go through here. We have the spec, which is more like the traditional MPI way of doing parallel programming, if you've ever done that. You have lab index, which tells you which worker you are working on, and you have num labs, which tells you the size of your pool, the number of workers you have. Those 2 variables you can use to create and build, say, for instance, your own CFD solver if you want to do that. Or, and you exchange data between the worker basically by sending messages to them. So worker this can send a message to worker that, and then you can share data in that way. Use composite arrays and stuff like that. Powerful Stim, yeah. StimD needs a power pool in order to run on the workers, of course. So it's just like powerful in that sense. If it's not, if you haven't started the power pool, it will be started. If that's the default behavior. And this is where you would want to have your parallel profile set up properly. So I will show you that, and then we shall have to call it a day, because I have another meeting soon. So I will show you in the screen of this one. Right. So what I'll do is I will start soonish. I will start Matlab here. Applications, Lunarc applications, Matlab. I'll take that one. Which node am I running on now? I'm running on this one, the ThinLink Arvis 01 client, because I didn't choose the hardware acceleration. Takes a little while. There are quite a lot of people logged in at the moment. Now, we're up. Now, you see in here, I hope you can see this, those of you who are following, there's a menu item called Parallel. So if I click on that, I have default cluster, in this case Aurora Local 2017B. You also notice that I have local and Matlab Parallel Cloud. Matlab Parallel Cloud is actually something that MathWorks provides for us. It's run on Amazon and it's included in our license. You can actually run Matlab code on your mobile phone or on your iPad or what have you using that. You just download their app. And then you can run Matlab on the beach if you want to. Been there, done that. You can discover clusters, you can have parallel preferences, manage cluster profiles, monitor jobs, license usage, cloud center, and so on and so forth. I will click on parallel preferences. So here is the default cluster. And here it says preferred number of workers in a parallel pool. This number is the number of workers that will be started if you do not state any number in par pool. And it will start 12. Do not have that to 500. I think that is actually the default. Because then you will start all of them. You will wait a long time in the queue and people will be upset. So have a look at that number, change it to something reasonable for you. I have it at 12 for historic reasons for me. You can set it to 20 if you want to, because that's the number of cores on a node. So you will take an entire node, which could be nice. So have a look at that number. You could also look at the shut down and delete parallel pool if it's idle. You don't want to have it hanging about for too long if you don't have to, because it will eat into your core hours that are allotted to you. So that's the preferences. You save and do whatever you much like with that. So I just canceling this. There are some other things. You can manage cluster profiles. This is the profile that's set when you run config cluster. As you see, it's set the number of workers available to cluster map is 500. Number of computational threads on each worker is 1. You can change that. Let's say you want to have a worker that have 20 threads. So send one worker to one node and it runs 20 threads. You could do that. The license number you don't have to care about. Those you don't have to get, files and folders. These are, have a look at these and you can see that there are a lot of things that could be interesting. Range of number of workers to run in number worker range is 1 to infinite, which is the default. That is 1 to 500 in our case. It will also, let's see, where is that? Yeah, the number of workers available to cluster 500. If you are running the validation, which you can do, it will use whatever number says here. So if you want to do the validation, change this number, because otherwise you start a job of 500 workers. You don't have to do the validation because it's this one. You don't have to do that because normally this will work. You only use this validation to see if it's something that is working or not working properly. So now this will take a bit of time because I was stupid enough to start it. Right? And finally, this thing, monitor jobs. This is a list of the jobs that you have or have recently run. If I'm to start another parallel pool here, let's see, par pool, and we start one of 3 workers, like so. Then it says it starts the local using the local profile, and you saw it turned up here, but now it failed because because we don't have any backend now because of the power outage. But you notice that it showed up there and then it disappeared. Right. Do we have any questions as of now? Because I really need to finish this up now.
So one question.
Yes.
Do you have a task option as in OpenMP to create task and parallelize according to that?
Yes, you can. The SPIMD would enable you to do that. The SPMD. So if you look at SPMD in the MathWorks tutorials, you would see that.
Okay.
Any other questions? Yep.
I have had problems with waiting for a job.
Yeah.
Just runs through and finishes the script.
Yeah. That was a bug. The bug was
Well, it was 2 days ago.
Yeah. The bug was fixed on Friday and implemented on Monday.
Okay.
So
I missed out on that.
yeah.
And now it's crashed, so I haven't had a chance to see.
Yeah. No. The problem was that actually a few problems. One of them was that we were using the OpenGL, the virtual GL, which in MATLAB's case, they can't use virtual GL because they use some of the more esoteric functions to get pretty graphics, which don't exist in virtual GL. That caused the program to crash. There's also a problem that for some reason our system account managers, the SACT system, was restarted in the spring, and then that means that it has job numbers that if you ask for the job number, you could get a previous job number that's finished. And that meant that your job, the job monitor, the system checking if this job is finished, would actually pick that number up, and it would crash on that because that job is finished and it's gone. So obviously I have to be finished. I don't have any output, so I don't know what to do. So we changed that now, so it has to match both the job number and your user account name. So that's highly unlikely that you will be receiving the same job number now as you have previously run a year ago. And we can't clean out the database because we need the statistics. So that's why we still keep it. But it should be fixed now.
So these batch objects, they're homemade by Lunarc. It's not a Matlab feature.
It's a Matlab feature that we created together with them. So the one who's actually written those is Raymond Norris at MathWorks.
But it's
together with me.
Specially adapted for the Lunarc creation.
Yes.
Which explains why I didn't find anything in the Matlab documentation.
No, you wouldn't. But that is the problem.
Now it's not a problem anymore.
No, now it's not a problem, but that was the problem. Right, any other questions? I'm sorry for you who are attending from afar because you won't get any freebies, but the rest of you will, even though you didn't answer the questions. If I just make one request for you who are attending from other places, would you please send me the names of the people who were watching, because we need that to report to SNCC for funding reasons. Okay?
Great.
Well, if nothing else, then that's all for now. So, goodbye.
Okay, thank you. I'll see you.
Yeah.